So hello dear students, today we will continue our second lecture of vibration and waves. Yesterday we have studied about simple harmonic oscillator. Simple harmonic oscillators are of two types, mechanical oscillator and electrical oscillator. So in the today's lecture we will study about a mechanical oscillator. A very simple example of mechanical oscillator is, consider a fixed rigid support and to this we have a spring of stiffness constant capital S, and to this spring a mass M is tied. This mass is stretched to this position and displacement produced is X. As the spring is stretched in the rightward direction, then this spring it will be experiencing a restoring force capital F in the leftward direction. So F and X, they are pointing in the opposite direction. So what we found, that the restoring force so developed, represented with the letter capital F, is directly proportional to the extension produced in the spring. Extension produced, we supposed this is equal to X in the spring. So we can write it like F is directly proportional to X. And if we wish to write it in equality, we add a constant of proportionality capital S here, where capital S is constant of proportionality, and it is called force constant, spring constant, or stiffness constant. And negative sign is due to the fact F and X are in opposite direction. So as clear from the diagram, spring is stretched in the leftward direction and restoring force is acting in the rightward direction. So force and extension are in the opposite sense. So now we have a new constant of proportionality capital S. So for this we will try to find two things: units of S. Second thing is definition of S. So for units of S in magnitude, we can write the formula as F is equal to Sx, because negative sign is due to the direction only. So it is F by X. So unit of S, it will be unit of F Newton, unit of X meter. So it will be Newton meter minus 1. So again, for definition also, in magnitude we can write S is equal to Fx, F is equal to Sx. So S is equal to F by X. So if X is equal to unity, then S will be equal to F. So from here we can write the definition by combining these two terms. The spring constant of a spring, the spring constant of a spring is defined as equal to S is equal to F, equal to, what is F? Restoring force, is equal to restoring force developed in the spring. Developed in the spring. Restoring force is automatically developed or produced in the spring when we stretch the spring. When spring is stretched by unity, X is equal to 1, mean spring is stretched by unity. So this completes our new parameter that we have introduced, spring constant. So this is our equation, F is equal to minus Sx, and S is the new parameter that we introduced, and we have studied its units as well as its definition. According to Newton's second law of motion, F is equal to ma, as acceleration is equal to rate of change of velocity. Further, velocity can be written as rate of change of displacement. So when we combine this, it will be the double derivative of displacement with respect to time. So we can write according to Newton's second law, of motion, F is equal to m d2x upon dt2. We mark it by equation number 2. So from equation number 1 and equation number 2, we get m d2x upon dt2, it is equal to minus sx so it is d2x upon dt2, it is equal to minus s by mx d2x upon dt2 plus s by mx. So after little simplification we reach here. So if we put s by m equal to omega naught square, So if we put S by M is equal to omega naught square, then the equation will change to this. So it is called differential equation of mechanical oscillator. So it is called differential equation of mechanical oscillator. And we mark this by equation number 3. So now we have to find its solution. So it is an ordinary differential equation. Its solution is given by x is equal to a cos omega naught t. So this is the solution of the above equation. We mark this as equation number 4. So you can check why this is the solution of the above equation. You put the value of x there and you will get it will satisfy the differential equation. Also, as we have substituted s over m is equal to omega naught square, so from here we can calculate the time period of the mechanical oscillator. So it will be equal to square root of s by m. So omega is equal to 2 pi by t. So t is equal to 2 pi under root m by s. So this is the expression for time period of the mechanical oscillator. So continuing further, we will calculate the kinetic energy, various parameters of mechanical oscillator. So next parameter is kinetic energy of the mechanical oscillator. For kinetic energy, because formula of kinetic energy is, we express it by uk. It is half mv square. So we have to find out the velocity. So velocity is derivative of x with respect to time, and for mechanical oscillator we assumed x is equal to a cos omega naught t. So a is a constant, derivative of cos is sin omega naught t into derivative of the angle. Omega naught comes common, this is minus a sin omega naught t. Omega comes common, it will be dt by dt, it will be 1. So omega comes forward, so it will be it is omega naught, sorry. So v is equal to minus a omega naught sin omega naught t. So this is the expression for velocity. We mark this as equation number 6 for mechanical oscillator. We will be needing this later on as well. So kinetic energy, we express it with the uk symbol, half mv square. So here we substitute the value of velocity from equation number 6. Yes, it is omega naught t square, and when we solve it, it is a square omega naught square sin square omega naught t. So this is the expression for kinetic energy. We mark this as equation number 7. So next is the expression for potential energy. We write it with the symbol UP, potential energy. And for this, we suppose of displacing. We go to the diagram of the mechanical oscillator. We displace the mechanical oscillator by a little of the distance dx further. and we try to find the work done for this small displacement dx. So small work done in producing displacement dx in the spring is given by, so small work done, it is force, restoring force and into displacement, and in magnitude we obtained F is equal to Sx, so dW it is equal to Sx dx. So total work done, because we have displaced the body from mean position to a position with the displacement x, so it is s x raised to power 1 dx. S comes common, integration is x square by 2. So we substitute the limits, upper limit, lower limit, so it is half sx square. This is the work done, and this work done is stored in the form of potential energy. This work done is stored in the form of potential energy in the spring. So instead of W we write UP, it is half Sx square, and here you can substitute the formula of x, it is A cos omega naught t, and S by M is equal to omega naught square, so S can be written as M omega naught square, so it is half M omega naught square A square cos square omega naught t. So this is the expression for potential energy, and we will write it by further equation, equation number 8. So now we come to total energy. U it is equal to UK kinetic energy, UP potential energy, so it is half M omega naught square A square sine square omega naught t. This is the expression for kinetic energy given by equation number 7. Potential energy given by equation number 8, it is visible to you. So half M omega naught square A square common sine square omega naught t cos square omega naught t. This is sine square plus cos square is 1. So U is equal to half M omega naught square A square into 1. So this is the expression for total energy. So dear students, this completes the first part for the mechanical oscillator. In this we calculated the restoring force, discussed about spring constant, then differential equation for the mechanical oscillator, expression for time period, then kinetic energy, potential energy, total energy. So this completes the first part. Second part are related to average value of kinetic energy, potential energy and total energy. It will be discussed in our next lecture, and there also we will try to solve few of the numericals related to the concept. So keep in touch. Thanks a lot for the today.